Alright, in a previous video we looked at Monge parametrized surfaces. So for example, if you had z is equal to f of xy, a surface given, in this case maybe it was cosine of x times y. Then you could create a Monge parametrized surface, which is a vector valued function, and essentially we are using u's and v's to represent, in this case, u is equal to our x variable and v is equal to the y variable. Okay, and then from that Monge parametrized surface we can compute partial derivatives ru cross rv, and that gives us something called the normal vector. And we can see in this example, and you can check for yourself, that the normal vector ru cross rv is v multiplied by uv, u sine of uv, and then 1. Okay, and what we're seeing here and how to interpret these results, if you're just drawing a general picture, just trying to get a sketch of what's going on here in the xyz space, you could choose a UV value. Choose a UV. So for example, maybe U is equal to 1 and V is equal to 2. Because we know from the Monge parametrized surface that U is in the X position, U is equal to X, we can also know then that X is equal to 1. And because V is equal to Y, V will also be equal to 2, and Y is equal to 2. Okay, so this is what we know is going on in the xy plane. X is 1 and y is 2. If you would like to figure out what your z value is, you would choose z and look at the z entry of the vector valued function. That would be cosine of uv, cosine of u times v, and z then would be equal to cosine u is equal to 1, v is equal to 2, so that will give you cosine of 2. So we know that we are at a location, right? If you find r of 1 comma 2, you get the point 1 comma 2 cosine of 2. And this is a point in the x, y, z space. So here we are at this point, r of 1 comma 2 in x, y, z space. Okay. There is also and if you do enough of those points, choose enough UV values, and every time you choose a UV, you are by default choosing an XY value. If you plot enough of those points, find enough of the Z values above those points, they look like this, right? Then you would create a surface, okay? And that r of u comma r of 1 comma 2 is one particular point on that surface. Okay? And then what about the normal vector? If you chose u is equal to 1 and v is equal to 2, you can then find the normal vector at that point 1, 2, which would be 2 times the sine of 2, 1 times the sine of 2, and then z is equal to 1. The interpretation of this is a vector. This is a vector at the point r of 1 comma 2. So it's a vector at this particular point, and we know it has to be normal to the surface, which means that it is the normal vector for the tangent plane to the surface at that point. And it could be one of these two vectors depending on how you computed the cross product. Okay? So that is what is true about Monge surfaces. Okay. We now need to begin looking at an interpretation of parametric surfaces in general. There are other surfaces descriptions besides the Monge parameterization. And here is a prototypical example that, let's say that we have r of u comma v, and we write u cosine of v u sine of v. And let's say that we write u squared cosine of v sine of v. Where did this come from? Okay, so what we're seeing here is that we're seeing three entries. Okay, and we're seeing that the first entry is supposed to be x is a function of uv, y is a function of uv, and z is a function of uv. So what we're seeing here is x is equal to u cosine of v, y is equal to u sine of v, and z is equal to u squared cosine of v sine of v, which if you're looking at these terms here, you can see is probably coming from u squared cosine of v sine of v is the same thing as x multiplied by y, when x is equal to u cosine of v and y is equal to u sine of v. So that's where this formula comes from. So part of these two entries are looking familiar to us. We've seen that the x is equal to u cosine of v before, except we probably saw that in the form of x is equal to r cosine theta, y is equal to r sine theta. So what we're saying here, when you're doing parametrized surfaces, the parameters that they typically use are u and v. But what we're seeing here is that u is playing the role of r, which is the radius of the circle, and v is playing the role of the angle, right? Putting these ideas together, we can see that we have a surface z is equal to x multiplied by y, but we have x and y given in polar coordinates. So we're seeing circles here in the xy plane, and then we are seeing the parametric form of the surface here is the part of the surface in blue that is sitting over top of these circles. Okay, so we're seeing a circular description of the surface x times y. Okay, so what we could have here is that you also have surfaces, perhaps x multiplied by y, but the first entry is u cosine of v, y is equal to u times the sine of v, and the function is evaluated at u cosine of v, and f is equal to u times the sine of v. That's the y entry of this function. Okay, and then we could plot this surface. Okay. Okay. And let's see. The u is the radius variable, so we probably like this. Let's see, why did that not plot like I expected? Okay, let's hold off on the normal vector. Okay, and let's see, u is the radius variable, so we'd like to plot this from circles going from radius 0 to maybe 3. Okay, and v is the angle variable, so let's let that go from 0 to 2 pi. Okay, and let me see, I'm not understanding why this surface is not plotting. Parametric plot 3D. U times cosine of v, u times sine of, I've got an extra, there we go. So here we have it. Okay, so again we have, if you look at this function from the top, you're going to see a circle in the xy plane. In the xy plane, you will see a circle whose radius u goes from 0 up to whatever number you wanted. So in this case, we chose u going from 0 up to 3. So this circle is of radius 3. and then v was the angle variable, and we let that go from 0 to 2 pi. And then because the z entry was x times y, but x was u cosine of v, y is u sine of v, we get that entry for the z. And here is the surface, but it's got kind of a circular shape to it because our values in the xy plane were only those points on a circle. Okay, so here you can get a circular description of a surface rather than a rectangular coordinates description of a surface. Okay, and it will still be true, okay, it is still true that if you take the cross product RU cross RV, okay, that you will get the normal vector to the surface, okay. This will be the normal vector to the surface R of u comma v, okay, at the point R of u comma v. Okay, so what we mean by that is that if you choose a specific value of u and v, let's try to do this now so we can let me go over here. Okay, so for this particular surface, let's choose a u value of 3 and a v value of 0. Okay, so we've chosen a radius of 3 and an angle theta of 0. Okay, if you plug in those values of u and v, okay, if you plug in those values of u and v, 3 for u and 0 for v, okay, you can do these computations yourself, you will get R of u comma v evaluated at u is equal to 3 and v is equal to 0. You will get R of 3 comma 0, which is the point 3 comma 0 comma 0. Okay, so R at 3 comma 0 is a point in the xy plane, xyz plane, and the x value is 3, the y value is 0, and the z value is 0. Okay, so if we were to look at a point on a circle of radius 3 and an angle of 0, right, that'd probably be this point right here, you could rotate that point out and see that it would be at the point 3, 0, 0 in the XYZ plane. Okay. Now, what we have is also the cross product. Okay, and here is a kind of a complicated expression for the cross product. Okay, and if you evaluate the cross product at the point 3, 0, okay, so if you look at the normal vector n evaluated at the point u equal to 3, v equals 0, you will get the point 0, negative 9, 3, which is going to be a vector at this point, okay? And when you put those together, you will have a surface description, a surface, and at that point, there will be a normal vector, n, which is perpendicular to the surface. Okay, so it's kind of complicated, but I just wanted to show that the same formulas that hold for the Monge parameterization hold for general parametric surfaces, that RU cross RV is one of the two normal vectors. It is the black arrow or the pink arrow, but they're both pointing normal to the surface. So ends this introductory video to more general surfaces described in essentially polar coordinates. the polar coordinates description of a surface.